Hello, in this video, we are going to give a justification for the divergence theorem. So remember that the divergence theorem said that if E is a simple solid region in R3 with a boundary S that has an outward pointing normal, and if F is a vector field with components, say P, Q, and R, whose component functions have continuous partial derivatives, over a domain that contains this region E, then the flux of that vector field, the flux of the vector field over S, is equal to the integral, the triple integral over the volume enclosed by S of the divergence of F. So again, the vector field, we're going to take the vector field to have components P, Q, and R, and that I can write it this way. And we know that the divergence of F is dp dx plus dq dy plus dr dz. So what we're going to do is we're going to take each side and expand it. And so we take this side, expand it, this side and expand it, and then try to show that the two sides are equal. So this is proof. So as I said, we're going to take the left-hand side, and I'm going to rewrite it. So left-hand side is the double integral over S of f dot ds. So this integral, bearing in mind that our f can be written in this way, I can separate that into three subintegrals. So I'm going to write this as the integral over s of pi hat dotted with n, because that's what it means to dot with ds and ds, plus the double integral over s of q j hat dotted with n ds, plus the double integral over s again of r k hat, oops, that's an ugly k, dotted with n ds. So that has three summands. We're going to take the right-hand side and do the same thing to it. So the right-hand side is going to equal, well, it's equal to, well, let me rewrite it. So it's the integral over E of the divergence of F dV. So I can first rewrite it as the integral over E, and I know what the divergence is, dP dx plus dQ dy plus dr dz dV. All right, so this one is not completely done. It's got three terms in it, so I can separate this one into three separate integrals. So this one is going to equal the triple integral over E of dP dx dV plus the triple integral over E of dQ dx dV plus the triple integral over E of dr dz dV. And I just noticed that this one should be a y. All right, so I have three summands in the first integral, three summands in the second integral. And wouldn't it be nice if I can equate those pieces that seem to be equal? So indeed they are. So I'm going to label these. So let's say I'm going to call this 1. This is going to be 2. And this is going to be 3. And below, I'm going to label this A, and this B, and this C. So the way the proof goes is that, at least in some special cases, I can show that this, I can show that this integral, the surface integral of P I hat dot and ds, is equal to this integral here, the triple integral over E of dP dx. And this one is equal to that one, and this one is equal to this one. So we would like to show that Uh, 1 is equal to A, 2 is equal to B, and 3 is equal to C. Now, the only part we're going to do, but all the parts are similar, the only part we're going to do is we're going to do this one. So, namely, what we're going to show is that the integral over E of dr dz integrated with respect to the volume is equal to the integral over the surface S of r k hat dot n ds. So I need a second page to do that. So let me pause for a second. For this to work, we're going to assume that here's our surface S, and we're going to assume that the top part of S is given as so it's a type 1 region. So the top part, which is labeled S2, Z may be written as some function U2 of X and Y. The bottom part, which is S1, may be written, and that Z may be written as U1 of X and Y. And then we have the side S3. So when we compute this integral, we're going to have to subdivide our surface into 3 pieces: top, bottom, and the sides. And we need to compute this dot product and do the surface integral. And for this part, we're going to use the fundamental theorem of calculus. So let's go ahead and do it. So we want to prove that r k hat dot n ds is equal to the triple integral over the region A of the partial derivative of r with respect to z integrated with respect to the volume. So we're going to take the right-hand side. And so that again is the integral over E of dr dz dv. Now, we can rewrite this as a double integral. We're going to use the fundamental theorem of calculus, but first let me rewrite it. So I'm going to rewrite this as using the fundamental theorem of calculus as the integral over D, where D is the region that S projects to, or E projects to rather, this region here in the plane. And then for Z, I actually have some limits. So the lower limit for Z is U1 of XY. The upper limit is U2 of XY. And then we have dr dz, and then dz, and then we have to integrate with respect to X and Y, so I'm going to write that as dA. All right, so this piece here, that integral, I could do out using the fundamental theorem of calculus. So what I can do is I can write this as the double integral over D of, all right, so fundamental theorem of calculus says that I'm going to get R, oops, sorry about that, technical issues. All right. So the fundamental theorem of calculus says that when I do this out, when I integrate with respect to Z, I'm going to get R at X, Y, and U2 of XY minus the final value minus the initial value. So I'll have R at X, Y, and the upper limit of integration, which was U2 of X and Y. And then minus R at XY and U sub 1 of XY. And that is multiplied by dA. And obviously I can separate this into 2 integrals, but that's the right-hand side. Now we're going to do the same thing with the left-hand side, or we're going to not do the same thing, but we're going to expand the left-hand side. So the left-hand side was equal to the double integral over S of R uh, dotted, or sorry, RK dotted with N ds. Now, S is made up of three surfaces. S3, which is on the side, S2, which is on the top, and S1, which is on the bottom. So we have to find normals to each one of those pieces. So what we notice is that the normal, so on, let's say, like on S1, then, well, S1 is on the bottom. So the normal vector to S1 is going to be minus k hat because it points down. On S2, the normal vector, it just points straight up. So it's going to be k hat for the unit normal. And the other thing that we need to do is for S3, well, it points in different directions, but really we don't care because what we know is that when we dot, what we know about the normal vector to S3, which is on the side, we know that that's going to be perpendicular to k hat. So for that side, the dot product is equal to 0. So we're going to rewrite this as the integral over S1 of, we said it's R. So then on S1, it's going to be R. The normal is on S1 is minus K. So R dotted with, so K dotted with minus K is going to be -1. So we're going to get negative R. And let's go ahead and actually do the dot product. So it's going to be negative R. The value of R on S1 is going to be U1 of X and Y, the value of Z. And that's going to be over the domain D times dA. So that's the first part. Then, so this is on S, this is from S1. And that's going to be plus the double integral over D of, so now on D, R, the normal component is K hat. So K hat dotted with K hat is 1. So it's going to be R at X, Y, and U2 of X and Y dA. So that's from S2. I should say from. All right, and we know that on the side, because the normal vector is perpendicular to k hat, the dot product is going to give us 0. So there's no contribution for the third side to the flux. So therefore, the left-hand side, if we look at these, so therefore, this is equal to this. So therefore, the left-hand side is equal to right-hand side. So we proved that this surface integral is equal to this volume integral, and that's the other two equalities are done in a similar fashion. So that proves the divergence theorem, at least for the cases where E is like a simple region.